Okay, hi. So today, just a brief introduction. I'm Zxiang. You can call me Z, and this is R. So we're going to talk about JavaScript-based event-driven physical computing. So just a quick introduction. I know you might have seen this before. So what is event-driven programming? So basically, it's a programming paradigm where the flow of the programming is determined by events. So like mouse clicks, sensor outputs, or messages from other programs, client requests to servers, etc. So in pseudocode, what you should see for this kind of event-driven programming style is you have a main loop that keeps looping, and it just tries to listen to inputs from hardware or from another computer or from some client. And after that, it produces a response when that event triggers. So, so for this kind of programming, this is the pseudocode that you should see in like C or something. But if you want to use like Node.js and other frameworks, usually the code for event checking, which is this part, in the main loop does not depend on application. That means for example, in Node.js, you will not see this main loop. You don't have to write it. It's basically running in the background. So for most programming frameworks, what you need to do as a user, you just need to implement the event handlers. So you need to write the event handler portion. You don't need to really bother too much about this. As you will see later in the sample code for Node.js, you don't see this main loop. So the agenda for today, I'm going to talk about three things. One of them is Node.js. After that, we'll talk about socket.io and Cylon.js. So this is the agenda for today. Okay, Node.js. Node.js, basically the applications are written in JavaScript and can be run within the Node.js runtime in OS X, Windows, Linux, or FreeBSD. So what we're going to do, because both of us have Windows, as in the demo is on Windows, so we're going to run the demo on Windows and we'll show you roughly how to run it. So what Node.js does, it basically maintains an event loop that handles all the asynchronous operations. That means if there's an event that triggers, Node.js just basically handles that. All you need to do is just write what you want to do with that event. IO requests are handled in non-blocking fashion in a single thread. What this means is if there's a lot of computation involved in a single event handler, it is possible to actually choke up the thread and cause problems for all the other clients. So for example, if you have a long set of computation for one particular event, it may cause problems when you run it under Node.js. So for Node.js, it's not used for every single application in mind. Basically, what you want to use it for is like events that can be handled quickly in short chunks of code. So Node.js is also able to keep many connections alive without having to reject new incoming requests for connections. So this is sort of the framework comparison between traditional and also Node.js, what it does. Under traditional server, what it does is you have a lot of requests. Let's say 1, 2, 3, 4, 5 requests. And then they will have like multiple threads that try to handle these requests. But for Node.js, what it does is it just only has one thread and it handles every single request asynchronously. So that is what Node.js does. So a sample code, this is basically a hello world version of Node.js. So a simple server. So you have a function. So on request, you'll produce a response. So console.log is basically the for you to debug stuff. So it's like you try to output some sort of message into the console, so you can check like if there's anything going on in the command prompt. So what this thing does is it try to take a client request or server request from a client, and then it tries to respond with hello world. So it writes hello world, and then the response ends. So so this is the event handler portion, and then after that you have to create a server on request. So it listens to this port 888, and then the last line is just to indicate that the server is running. This is more for debugging purposes, so that you know that the code is actually running. So we will demo this.
And very importantly, after that it goes into the event loop.
Sorry?
After console.log, it goes into the event loop, right?
Yeah, it goes into a loop that checks for events. So if you look at this code, you do not see any sort of like while loop or anything that checks for the event. So basically, that's what I mean when I say that the event is being handled by the program itself. You don't need to write it out specifically. So So support for periodic events. So this is just to show you why Node.js is so good for handling time-based events. So in C, for example, if you want to do a while loop and you want to sleep for maybe 1 second, and then you want to print high, for Node.js, you look at this. So you have a function, and then set interval of 1 second, and you alert high. So what this does, these two code actually does the same thing. What it does is, every 1 second, you just try to say hi. So it just like writes hi in the output. So if you look at this, there's no clear advantage comparison between C and Node.js. I mean, the length of the code is almost the same. But if you try to do something more complicated, so basically what you have is, you have one function that says hi, and another function that says hello. And you try to set it to like, to write that response every 1 second and another one at 1.5 seconds. If you do it in C, what you have to do is you have to do the LCM of it. So you have to have like 1 second sleep and then high, and then 500, just 500 milliseconds, and then after that hello again, and so on and so forth. So you can see that if there are more requests over here, the equivalent version in C will be extremely long. So you need to handle all these things in C yourself. Whereas for Node.js, you don't need to. You can just write it in a simple manner and it will work. So that's the
just to add on that. Basically here in C, you can simply do is you can run these two particular functions on different threads, and you should be good enough. You can write a shorter length code, but threads are more overhead then. So your CPU resources will be used more in cases of thread. Whereas in Node.js, it just time multiplexes the CPU, and everything runs on a single thread. And if you want to create interrupts here, that is again a long piece of code. So you can see for software events, it's so easy to maintain in Node.js. So yeah, so
Socket.
Quickly running into Socket.io. So it's a framework of Node.js itself, and I have just to take a print screen of the front page of its website, and it emphasizes what exactly the purpose Socket.io is very famous. So if you go to the first line, it says that it enables real-time, bidirectional, and event-based communication. So Socket.io, you can do this, where server and client has to talk with each other. You can do this kind of stuff very easily using Socket.io. And it works on every platform and browser. Now, these are the 4 applications which is, just you can do it in few lines of code with using Socket.io. So one is real-time analytics. This is, very relevant to something that you will use for embedded devices. You have inputs coming from, or the readings coming from the sensor, and you want to plot a chart according to that. Then you can use some Node.js frameworks again and use Socket.io on top of that to, with just few lines, you can create a chart out of it. And I'll go through this chat application that is coded in Socket.io next slide. And you can see it's just, a few lines. And again, with Socket.io, this has become very easy that you can send an entire chunk of image or audio or video in the binary stream. So you don't have to use JSON or anything. You can just send via type binary. And again, for Google Docs and stuff like that, Socket.io is used. So this is the chat code for Socket.io. And so first, I'll just briefly tell you guys about Express. So Express is again a framework for Node.js, and with it you can basically handle server and client very easily. So with this just single line, you can create a HTTP server, and this is the handler for the same server, where you just say whenever you get a response, you send it to the client file index.html, and you are going to listen to a client, which is, you can just open localhost 3000, and it will basically contact to the server. So on the client side, I removed the head part, which is just formatting of the web page. In body, your main script lies of Socket.io, and you just create again an object of Socket, and every time you press the send button, which means you submit the form, you just emit a chat message of whatever was written in your chat window, and you can create an event here your whatever name you like. Here it calls it chat message. So after your message is emitted, you clear your chat box, and then on this side, so first Socket.io has some event handlers. I mean, events like connection or disconnection can be handled, just using this keyword. And after that, once you are connected to the client, you can wait for this event chat message. And as soon as you receive this event, you are just going to emit the same message to all the other clients that are those are active. And here also on receiving the chat message from the server, it's just going to append it to the message list that is getting printed on top of the page. So this is it. You can build your chat application.
So in this case, you have server talking to something which is browser based.
Right.
In a more typical scenario where I have, let's say, sensors coming to a platform and then I'm talking to a backend server.
Okay.
So would both be written in Node.js? Is that how it will work? That is my stuff which is talking with the sensors and then pushing the data back, and then my server which is doing something. Will they both be Node.js?
I'm not sure about that, but should be, because this is something that you are going to create an HTTP server and then HTML will run on top of it. Or you can use Cyclone.js for the platforms those are supported.
I guess my question was the following: that if I don't have my client being a browser kind of stuff, right? If my client itself is some program, what would it look like? What would I write that in?
So do you?
You know what I'm saying?
I got your question.
This is stuff running on my Raspberry Pi.
Right.
Okay, talking to a sensor.
Right.
So it gets the sensor data. Okay, and then it's pushing it out, and the equivalent of your message append might be an actuator command or something like that, right? So this makes sense when the client is a browser. What happens if my client is not a browser but it's actually an embedded device?
I see. Right. So I'm not sure about this. I mean, we haven't come across those examples, but I'm pretty sure there will be a framework which can handle, something that is running not on a web page. So yeah, I can get back to you on that. Okay. So yeah, next we have Cylon.js. So this is again a Node.js framework for, this is mainly used for robotics and physical computing. That is the embedded devices that we are using right now that can be, programmed with using Cylon.js. And you can control and connect many bots together, and you can control it either using your computer itself, the code running on your computer, or it can again interact to the website, whereas you press buttons on a website and your device will run accordingly. So this is a snapshot of the architecture of Cylon.js, which makes it possible. So it has a main control program, which talks to the API of Cylon.js itself. So this main control program connects you to the various bots, where you can mention which adapter you are using and how the bots are actually connected to the MCP. And API then further, contact to HTTP or WebSockets, and you can control it. So as of now, it supports 31 different platforms and many of the I/O devices. So it unfortunately doesn't support Mbed, but Arduino, Raspberry Pi, BeagleBone, Nest keyboard, it supports platforms like that. And in case of I/O, it can control a sensor or LED or motor or switch. So this is again a simple Hello World example of Cylon.js. So as usual, you just create an instantiation of Cylon, and then you create a bot on Cylon, and after that you have basically access to all these keywords. So you mentioned what connection you are going to use. So you will specify the board name, then the adapter that you are going to use, and which port it is connected to. And again, you can basically instantiate multiple platforms and devices here. So you are again going to do the same for an LED, and you'll be specifying which pin it is going to connect to. And so this is something that Cylon.js has created a wrapper on top of set interval that we went through in the periodic event example. And you can easily here say every 1 second, just toggle LED. And my something similar that you used to, you use this in Java or any object-oriented programming. So my just refers to this particular device that you have instantiated. So it will just toggle the LED every 1 second. And you just start this process. So we went through, the demos and examples of all these three, Node.js and its frameworks. So this is just what we feel about it. So one thing is it's very easy to install and play with across different, OSs. So for Node.js, you can go to its website and create a Node command prompt. And after that, you can use something called npm install and, install various frameworks of Node.js. And again, these frameworks are, maintained for making your life really easy. The code becomes really shorter, and the learning curve is not that much. You can easily find examples of that. And many complex codes are also maintained in GitHub. So if you want to leverage something from there, you can do it pretty easily. Now on the other side, this is something that has come out very recently, and many of the frameworks are new and they are prone to changes. So Express is something that changed very recently. So some of the codes that we found on GitHub were just outdated, and when we tried to run it using the Express that is available now, that didn't work. And on Cylon.js, some of the platforms are, that requires Unix files to compile. So we are unfortunately not able to, for example, Raspberry Pi and BeagleBone, we were not able to install it on a Windows system. So that's about it. And these are some references if you want to, just start by yourself what, Node.js and these frameworks are. You can simply go to its website, and it has many resources by itself. And, this is again a very interesting video by the creator of Node.js himself. And, it's a 1-hour tutorial sort of. And you can go through that. So yeah, that's about it. And now we'll go through some demos.
So basically for the demos, so chat service is the one that we will use both Node.js and I/O. This is the simplest version, the Hello World version in Node.js, which I talked about just now. And the last one is more interesting. This is like a counter. So what it does is every time it accepts a server request, for example, you use a browser to do a server request, it will increment a counter, and you will see, and it will be charted out using smoothie charts. And then later on, you will see smoothie charts is basically just a charting tool in JavaScript. And you will see that every time there's an incoming request, the chart will bump up by 1. So that means there's an increment of one server request. So this is the code that I think I've talked about just now, where we had to modify it to sort of hack it to get it to work with the latest version of Express. Because when you install Express, the latest version is 4.x. The code is 2.0, so we had to hack it to get it to work. This is the source code in GitHub. So we're going to do the demo. Yeah, that's about it. So let's pull this out. So this is the simplest version. So this is the same code that I showed you, the Hello World version. I'm going to run it. So if you look at the, you can't see it over here, but let me see if I can move this thing slightly towards the right side. Yeah. Okay. You can see at the bottom, this is the console. So you can see that the console states that the server has started. And then after that, if you try to access it, maybe through here, yeah, it will show Hello World. So basically, this is just the simplest. Yeah, you can't see it.
It's there.
Yeah, it's there, but you can't really see it. Let me just move it over. Yeah, so you can see the Hello World stated there. So this is one. Yeah, and you can see at the bottom, now it says that request received. So there are 2 requests received. This is because for browsers, what they will do is they will first request for something called favicon. which is a favorite icon. That is the small icon that you see every time you try to access a website. So, for example, for Wikipedia, you'll see a small W on the left-hand side of the address. This top corner, usually you'll see it here. And then the second request will be the one where it actually does the HTTP request. So you always see 2 requests received when you try to attempt to like do a request to a server through a browser. So this is one thing. So I'm going to stop this, and then we'll show you the chat version of this. So I'm going to start the chat demo. Okay, so now it says it's listening on port 3000. And then, so for example, if I open two tabs accessing the same port on localhost, if you try to type something on one, you'll see it appear on the other. So let's say hi, and then you should see it on this side. So this is the simplest chat example that you can do with Node.js and Socket.io. So I'm going to stop this. And now the last one is basically the counter version. So this particular code will be closer to what you want to do in an embedded system. So I'm going to start it. Okay, as you can see, right now there's only one client connected. So you'll have one line, and then you'll see like the line moving as it updates. So if I try to put more requests to different tabs, you'll see that the line increased. So you'll see that now there are two requests or 2 connected clients. And then if I try to close it, it will go down again. So this is basically a simple demo of how Node.js does handles event-based stuff. So I'm going to go through the code a little bit. So there's a lot of initialization on top, which I will not go through. But the main chunk of the code is here. That is the counter portion. So you basically have a variable count, and then every time there's an incoming connection, you just increment count, and if it disconnects, then you just decrement. So then after that, you will pass this particular count. It will emit it to count as a variable, and then it will put into the it will pass that function into index.html again. So this is basically another HTML file, and then it lists on this particular port. So it will try to listen for any request on this particular port. And in the HTML file itself, basically what we use to chart it is something called smoothie charts. You can use this particular function if you want to chart anything like sensor data or whatever if you want to. It's basically a JavaScript charting tool. So the way to use it is you have to, of course, call it as a variable here. So you have a new smoothie chart, and then you just say, like, for example, what style of the stroke that you want, fill the color. I don't have a color, so I fill it with white. And then you can set like vertical sections, line width, and all the other stuff just to format the chart. And then after that, you can have a time series, and it just updates every 1,000. 1,000 means 1 second. So every second it will update, and can you see that? Yeah, it updates the chart every 1 second, and you can see live data feed from your sensor or client request in this case, whichever that you will attempt to do. So yeah, I think that's about it. Anything else you want to add? No.
That's it.
That's about it.
Thank you, guys.
Yeah.
Questions?
Any questions?
Sure. I'm sorry. Yeah, yeah. This example, yeah, it does use HTTP.
Well, socket IO does not. Is socket IO over HTTP or is socket IO opening a direct socket?
I think it's this. It is not on HTTP.
Yeah, so
It's
socket
express
IO
is
is
not.
not on HTTP.
Yeah.
Socket IO just uses sockets. Yeah. Ivan, you are shaking your head. So do you know?
Oh no, so yes, you're right because socket IO is actually nothing more than a wrapper over
Regular sockets.
Yeah,
that's
web
right. That's why you saw the function passing it into HTTP to do the query.
So there are two things going on out here, right? I mean, there is communication going on via HTTP, which is for the main web page and all, but then for the time series or whatever the count value going through, that is going over the sockets, and that's just the raw socket, nothing to do with HTTP. So what this is letting, which is how they're able to send binary stuff and all also. So it's just links. Yeah. So actually, this Node.js stuff has really sort of become extremely popular. I see a lot of embedded devices and all kind of using it. Partly, it's a very lightweight platform, which is why you see kind of it's ported to a lot of. It's been ported to a lot of Raspberry Pi, BeagleBone, all these kind of devices as well. But the other thing is there is also since it's all JavaScript, so it kind of melts very well with JavaScript inside your browsers and all. So a typical sort of product where you may have some device and talking to some sort of a server, and then sort of you have a web-based access to it, like this plotting and all these kind of things. It makes it pretty easy. There's just tons and tons of frameworks around it. So, and the other thing is the event-driven stuff can be can be very, very, very complicated. The first time, like whenever I've tried to work on it, you have to throw aside a lot of like your preconceptions about how the code will flow, because main thing out here is normally when you write a C program and all, you kind of do I/O. So you basically say read something from a file or things like that. Here it doesn't work like that. Your answer doesn't come back with the function when the function call returns. All your function call is doing is it is putting in a request for the task to be done, and then separately you have to have a handler to take care of things when the task is done. So write to a file, so you'll issue a write command, it will return immediately. But it is possible that the write has been delayed because the file was busy or whatever. It takes a long time to write. And then later on, the OS will send an event saying write done, and then you need to have a handler for that. So things where, so even though they showed that how C programming is very complicated relative to certain things, but for some other things, Node.js requires you to kind of think very differently. That everything is an event, every action is asynchronous, everything is a request to do something, and then separately an sort of an event will be generated whenever the task you issued will come back. But the nice thing is that it fits very well with kind of the asynchronous event model, which is very common in embedded devices. So, okay, so wanted to move back to the okay, so back to the clocks. So we looked at sort of various non-idealities that exist in clocks, and then I kind of made the point that ultimately stability is something that is very important, and you pay for stability in form of power and dollars. And there's a whole spectrum of technologies out there, which kind of range from microwatts to watts, and from cents to thousands of dollars. And depends on one's ability to pay. So for a variety of purposes, a whole bunch of different sort of clocks at different price points have emerged. Now, when it comes to characterizing what is how characterizing sort of how well a clock is doing or not, as we saw that one thing that matters quite a bit is over what time horizon you're looking at. So the drift that takes place in a clock, you could say that how much it is over a time window of interest. So two clocks may have very diametrically opposite characteristics over
long versus short time duration. So a measure which is used to capture this thing is something called Allen variance. So our Allen variance of a clock is basically saying how good it is over a particular time window of interest. So specifically it is defined as 1/2 of the time average of the squares of the differences between successive readings. So let's imagine I have a clock which is driving a counter and I'm reading the counter, and let's say that counter is called Y. So every time step I can read the counter and I'm going to get a new reading. So let's call it Y sub I. Allen variance has a parameter associated with it, tau, which is basically saying over what time window am I looking at things over. Okay. So Yn is now normalized average frequency over tau. So what I'm going to do is so I kind of misspoke. Let's say my counter is C sub I. What I'm going to do is I'm going to smooth it out. I'm going to take average over time windows of tau and call it Y sub I. So each window of length tau becomes its average becomes Y sub, we'll call that Y. And then we basically take the variance over that. So in effect, what we are doing is we are if tau was equal to 1, then it basically boils down to a regular definition of variance. But if tau is some other integer, then I'm basically doing it over longer windows. So main thing it is seeking to characterize is that I'm beginning to look at stability over longer time windows. Let's see if I have an example out here. Okay, so I was measuring. So this is kind of the real time. And I was looking at the count. So this is what the counter was showing. Okay, and it is advancing just about right, but not exactly the same. So what you see out here is the difference between successive readings. So this, so between successive pairs of readings, I'm going to get different frequencies, and you can see that they differ slightly. Some of it is simply the quantization error, but some of it is also because of the instability in the frequency. To calculate Allen variance over a particular tau, so let's say in this case tau equal to 3, what we do is we take groups of 3, average them, and this is the time series that we are going to work over. And that is the Y time series, and that's what we kind of calculate, and we get this particular Allen variance. So when you look at Allen variance of a clock, it would be defined at some particular time window, some particular tau. And that's what you're going to work with. So what you're seeing out here is kind of a data sheet that clock may have, where you are given tau in seconds, you are given the Allen deviation, and there are a bunch of different clocks which are shown. They basically correspond to different kind of things, as well as things like NTP, which is a network protocol. And what you see is that some of them do well at short taus, small taus. Some of them do well at long taus. So let's say, for example, if I look at this particular clock, it is good. It is short-term stable, but it begins to get bad at long term. Whereas if you look at NTP, it seems to have a long-term stability but short-term instability. So when selecting a clock, it becomes quite important that when you talk about stability, what time horizon you are talking about. Let's look. Next thing to look at is what are some of the technologies that are kind of available out there at this lowest level, the resonating element, and because that ultimately is what sort of plays a big role in this. So a whole bunch of options out there, ranging from just using basic circuit elements, inductor, capacitor, or resistor, capacitor type circuits, inverter rings, this I have mentioned before, quartz crystals that we have mentioned before, MEMS resonators. These are little mechanical structures that are built on integrated circuits, and they can resonate. So essentially you can make tuning forks and these kind of structures on silicon. Atomic clocks, and then there are a bunch of other things which have also sort of emerged. So a whole bunch of resonator technologies. Inverter ring is very commonly used because it's very easy to fabricate as part of your processor, and it's basically an odd number of inverters arranged in a loop, and so you can define the frequency in terms of the delays through these inverters. The problem with this kind of stuff is that the delay of gates has a strong dependence upon temperature, and also when these inverters are fabricated, not only are they not identical to each other, different copies of these on different chips are not going to be exactly the same. So it's very hard to design these things to give you an accurate frequency and to give a frequency which is going to be stable. The flip side though is that you can get very high frequencies very easily on chip. You don't have to feed them from your printed circuit board into the chip. You can locally generate these things, essentially zero cost, but flip side is very unstable. So like the stability could be like hundreds of thousands of ppm. So they're pretty bad. But for a lot of times, all you want is something running fast or something just running. Okay, you don't really care about the stability. And maybe the stability could be then achieved by disciplining this clock. That is, you can have a processor running this clock, but then separately you can run some sort of a protocol, maybe NTP or something, which frequently synchronizes from something outside, and thereby keep this clock keeps correcting for this for the drift out there. Quartz crystal are the workhorse. So literally, it's a crystal of quartz which has been cut along a particular angle. So if you recall your physical chemistry kind of courses and all, crystals have certain planes. So depending upon which plane you cut this particular crystal in, it will have a different resonating frequency. And so literally, these are very accurately cut crystals. And the nice thing is that they are much better than kind of preceding approach of inverters, very high stability. You can easily get these things in tens of ppms. Now, other characteristics are also very good. Some very strong resonance, for example, very low jitter. These kind of characteristics are there. Some angles of these crystals are very good, some are not. So, but they again suffer from the same issue that this is a manufacturing process. So you're taking crystals, cutting them, polishing them. So there are going to be variations, and there is, of course, still some temperature dependence also. Disadvantages: they're expensive because this is a mechanical fabrication process. The other issue, so there is variation from crystal to crystal, and any to get them very accurate, you need to do a lot of calibration. So they are kind of painful. Tuning forks. This is what is used in real-time clocks, so very low frequency type clocks. Literally, it's a tuning fork. It's a little mechanical structure. Can be made on silicon, can be made otherwise, and they're kind of used for low frequency stuff. Good stability, good power characteristics, but low frequency. So all of these resonators have some temperature dependence. In many cases, they're very nicely behaved. So like, for example, for a tuning fork, temperature dependence is a very nice kind of a quadratic or cubic kind of shape that you would see. Crystal oscillators show a cubic phase. So the nice thing is that these are well understood physical structures, and therefore to calibrate them, it actually, all you need to do is to learn this curve. And learning this curve could be done in the factory, so you kind of test it at different temperatures, literally put the clock in a oven with a controlled temperature, see what its accuracy is relative to a test instrument, and now you have with a few measurements, you can learn the curve for a particular resonator, store it in a little memory along with it, and then have a temperature sensor and then correct for it. So that's kind of, you can correct for these things relatively easily. So tuning fork is quadratic, quartz crystal has a cubic structure, but they all kind of work the same way. The problem though is that this calibration requires effort in the sense that each part has to be calibrated separately, and therefore they add to the cost. So you can buy these things, and if they are pre-calibrated and all, that is when they begin to be called temperature compensated, and that's what costs you money. This is for quartz crystal, so you see kind of same kind of phenomenon, temperature versus stability. In this case, the curve is quadratic in shape, and what these different curves are corresponding to is errors in the cut. So there is a cut which has no error, but then each one of these correspond to a different 1 minute error in the cut angle. So they basically correspond to these things. So when you buy a crystal, if you're lucky, you will get the nominal one, but if not, you're going to get things on one of these other curves. And again, you can either calibrate them or you can pay to buy a pre-calibrated crystal. So crystals have many different planes. They go by name of Z cut, SC cut, things like that, and they all have different characteristics, but they all kind of have the basic sort of temperature dependence that sort of existed. So that brings to the issue that one way to get stability is to buy pre-calibrated stuff and then pre-calibrating with some compensation circuitry around it. So these things are called as temperature compensated clocks, or so there are three names which you will see out there: TCXOs, analog type, microprocessor control stuff, digital TCXOs, and then oven control things. So what is happening out here is that in temperature in this one, basically essentially what you have is an analog circuit which measures temperature and then changes some characteristic of the circuit so that you compensate for the instability that is occurring. And these things are calibrated. So in particular, certain resistance values, literally potentiometers, they are calibrated in the factory. So they will take the stuff, subject it to certain number of temperature settings, see what was the drift, come up with what the compensation setting should be, tweak this analog circuitry, and then ship the product. And that suddenly raises the cost from literally a few cents to a few dollars, okay, because you're not putting in effort on it. Digital stuff works the same way, except that now instead of having this analog circuitry, literally what you have is a temperature sensor, which essentially looks up in a table and says how much compensation to apply, and then essentially changes the capacitance accordingly, which affects the frequency. So again, you are doing fine tuning to the frequency. And then the final one, the most expensive stuff, is this oven control thing, where literally inside the package there is an oven. By that, what I mean is there is some way of generating heat, and that you can control so that you can keep the temperature constant. There is a temperature sensor, and thereby you keep the crystal in a very temperature controlled setting so that it's known to operate at a particular curve. Next up, in terms of stability and also, so by the time you hit OCXOs, you may be $100 type thing. Next up are atomic clocks, and of course, normally when we think of atomic clocks, we think of them as like huge room-sized things, and that's indeed how they always were until very recently. But the basic idea in this thing is it is atomic resonator, literally something which has some cesium or something like that suspended, and then you are letting the atoms oscillate, and then you are sort of measuring those oscillations, and then eventually somehow you're going to take this out, to go through some other circuitry, and finally you use that to correct a quartz crystal. So the idea is that you're actually going to be reading from a quartz crystal oscillator, but it is being continually corrected by the atomic clock, the oscillations of the atoms. Now, early stuff were big, huge, room-sized things and all, and they are still kind of the best thing which is out there. Some 10 years ago or so, the Department of Defense sort of concluded that it would be cool to have, or very useful to have, very high accuracy, very high stability clocks in very small packages. And there are several very good applications for it. Sensor packages which are deep under ocean, they need to maintain time for long durations of time, otherwise they have to communicate out. Again, things which could be put on missiles so that navigation accuracy is improved, handheld radios, because if they can synchronize very easily, you can imagine things like a device can go to sleep saying, I'm going to wake up and communicate. So the two parties can say, we'll wake up a month from now and I'll send you bits. And if the clocks are very stable, then you wake up and just start squirting out the bits. You don't have to do any synchronization at that stage. So you can kind of get great advantages that way. So all of that led to so-called chip-scale atomic clocks. You can see how tiny they are. There's a quarter out here. This is a chip-scale atomic clock. The cost, $1,500. consumes around 100 milliwatt, 75 milliwatt, something in that range. So it's still power hungry. I mean, a lot of our embedded systems are in single-digit milliwatts, so this is certainly an order of magnitude more. But on the other hand, for many other applications, this is great. $1,500, pretty expensive. Again, you're not going to put it into a $1 sensor, but for a lot of other products, it's very it's very good. So literally, what they do is they create a whole physics package inside this, okay, about which I really know nothing, but they have a tiny little atomic clock, not as good as this room level stuff, another maybe a couple of order of magnitude worse, but it is 10 to 100x better than anything else that you can kind of buy. So great improvement. So this is where basically what we stand at this stage, that for most routine stuff, crystal oscillator, or actually even perhaps just your on-chip ring inverter kind of stuff, if you are into sort of networking kind of stuff and all, you will need to need PCXOs. Test instruments and all, they use OCXOs. So if you have kind of expensive lab grade instruments and all, a lot of stuff out there is now using the chip scale atomic clock. But this is not, you can just go out and buy. Very few companies sell it. They're export controlled and all. And then finally, inside, like for applications like the GPS satellites, each GPS satellite has an atomic clock in it, for example. Okay, so there are applications where you really need that high degree of stability. So ultimately, penalty of all of this thing is power and cost. And this is a plot from Professor which kind of shows where some of the current technologies kind of stand. So you can easily have power numbers going all the way to hundreds of watt, but stability you can get to 10 part per trillion. Okay, so pretty amazing kind of things, but then you are looking at room level kind of atomic clocks and all. And likewise for the cost, you can easily go from pennies to thousands of dollars. So disruptive new technology which has come out in recent years is the so-called MEMS resonators. So which MEMS, those of you who don't know, stands for micro electromechanical. So they basically are the ability to make mechanical structures in silicon on chip right next to your rest of your digital and analog circuitry. There are many different ways it's doing, but the basic idea is the following, that you create mechanical structures which can resonate. Okay, so literally you can imagine making a tuning fork, for example, or some other pendulum, for example. So you can make these kind of structures and then get clocks out of them. There are electrostatic type approaches, there are piezoelectric type approaches. Main beauty of these things is your clock is sitting right next to your circuitry. So you don't have any additional package outside. You don't have to feed the clock from outside. Saves on board area. You can throw, even though the resonators may not be as that good, but you can now throw processing at it, more signal processing, more control to get more stability out of them. So there are a lot of interesting stuffs happening around this. They also have some advantages beyond size and all also. So for example, they are less susceptible to shock and acceleration and these kind of things as opposed to packages which are sitting elsewhere. So relative to quartz crystal and all, they have some significant advantages too. So MEMS, these are just showing some pictures and all, but the main thing is size and cost, particularly for applications like smartphones and all, where every little saving of board area matters. You can get into very high frequencies. Flip side, the main flip side is that these things have been around for a very short time currently. So what the long-term stabilities and all are still not as well understood. So time would tell how they do, but they are an attractive new technology. So now you can imagine that if clocks become cheap and high quality, suddenly you can design systems and all where you can put, you need a different kind of clock, you can put it there, you can make them highly programmable. They don't cost tiny corner of the silicon, so they don't cost dollar, they don't cost volume, they don't cost much in power. So they essentially give you cheap clocks everywhere. Now, one thing to keep in mind also is that the frequencies that you use in the system may not be the same as what your clock provides. So if you look at any typical processor, they will usually also have some circuitry which takes the clock that you're providing it, and that clock that you're providing it could be coming from an external source like a crystal oscillator, could be an on-chip source such as the ring oscillator, but then you are going to feed it into some block which you can program and then get the desired frequency. In fact, in any given application, you may need multiple clocks. Like for example, if you have USB, it needs a particular clock, your main processor may need a different clock. So a very crucial part of these systems is usually some circuitry which lets you change the clock frequency. So clock frequency division is easy, right? I mean, I can just feed it through a series of flip-flops and multiply or divide down the clock frequency. So I have high frequency clock. From that, I can derive lower frequency clocks as long as they are well-behaved, well-behaved in terms of they are divided by some integer value, for example. But when it comes to getting more complicated frequencies, like for example, I need a higher frequency than what my clock is, or if I need a frequency which is a very odd multiplication, like 2/3 of the frequency or things like that, then you begin to need some more sophisticated circuit. Bear in mind that even though we operate our processors at, let's say, gigahertz, 2 gigahertz, 3 gigahertz, there is no such thing as a 1 gigahertz crystal. Your crystals are 40, 50, 100 megahertz. So internally, you have to multiply things out. And that is done using these things called PLLs, or phase lock loops. And this is something that some of you may have seen, but those who haven't. And the basic concept is like the following. I have some clock source, crystal oscillator, which is presumably at some frequency which is natural, right? I mean, you cannot get arbitrary frequencies. So when the quartz crystal is cut, there are certain frequencies that are commonly available, and that's what you have. What I want is a high frequency clock, or a clock which has some other funky relationship. Like let's say, for example, in general I need, for now let's imagine I need some n times this frequency, where n is a higher number. So I need a higher frequency in this case. So what we do is the following. We have a circuitry which detects the phase difference between a signal out here and a signal out here. Essentially, it says that do I have identical signal here and identical signal here or not. This error we smooth that error out, and we feed it into a voltage controlled oscillator, an oscillator whose frequency can be affected by changing the voltage. And there are many easy ways of doing this thing. Even your quartz crystal oscillators can act in that way, but there are the simple circuitries that you can make where the voltage affects the frequency. So this thing could be unstable. But main thing is, so I have this voltage control oscillator, and the idea is we design it such that it produces, it is seeking to produce a high frequency clock. And then we take this signal, we divide it by n. We know division very well. We can divide a digital clock very well. So if this guy, if this signal is identical to this, and this is divided by n, that means this must be n times the signal out here. So by closing this feedback loop, I basically end up generating a signal which is n times out here. And the same concept can be applied for an arbitrary division also. So there are these things called fractional PLLs, but the idea is that you can literally generate some rational number multiplied by this frequency in the output. So I can generate arbitrary ratios out there by properly designing this particular circuitry. So almost every modern processor you would have a PLL, so that you can internally generate a high frequency clock. You can internally generate all those other weird frequencies which are needed for things like USB and other type of interfaces, even though you may have a single source out here. And then nice thing is that all these clocks you're generating, they're all nicely synchronized because they're all coming out from the same source. If on the other hand you had different clock sources for each one of them, then your USB frequency will not be synchronized. The clock will not exactly be following the clock of the processor, and all sort of bad things can begin to happen. So PLLs are a crucial part of these things. And if you look at any processor, including the one on embeds and all, you would see that they have a pretty elaborate clocking subsystem where you can program them, you can set the frequency at which your processor is operating. You can select what the source is. You can say it is a crystal oscillator or some other source, external or internal, and all those kind of games can be made. Go ahead.
About the phase change. If the phase change is 1 billion, how can we?
Yeah. So firstly, what we're seeking to do is get a frequency. Okay. So think of this phase detector as basically saying, I expect this clock and this clock to be the same, right? Because this clock, we are claiming that this is n times f ref. We are divided by n, so this clock, we would expect it to be the same as this clock. This guy is very stable, so my goal is to have this guy aligned with this, okay? So if their frequencies are matched and if the clocks are toggling at the same time, then their edges should be perfectly aligned, and therefore any gap between their edges is an error. And if I can drive that error down to 0, then I am in good shape, because if I can make this signal identical to this, then this signal would be automatically n times that. So driving down the phase to 0 is also ensuring that frequency here and here are aligned.
Yes, I think phase detector, if there are 1 billion shifts, there is no problem, as we don't need to be on the same time.
Okay. There could be a 1 period shift, but that is fine. All we are so we are not maintaining time; we are maintaining frequency. Okay. Now, even with this, what you may happen is, because these circuitries are not perfect, this is basically not a very stable thing. So you would see that there will always be some jitter, like any control system, right? I mean, if you design a control system where you want to maintain, I don't know, the speed of a vehicle to be a particular value, it's not like it just maintains, it goes there and hits that value, it oscillates around it, there is convergence, there is some residual error. All those things happen out here. So there will be an issue with these kind of things is that the edges out here, they have a lot of noise in it, like they jitter quite a bit and all. But the point you are making is that I can have a 1 cycle error. Okay, so it is, but that in this view is not an error, because we are not worrying about time, we are worrying about frequency. Okay, so there is no such thing as a cycle error, I guess, in this. So that's how PLLs work. So you can multiply frequencies, you can divide frequencies, and by appropriate combination of the two, you can have arbitrary rational numbers. Okay, and that's what are called as fractional PLLs. Now, this gives, so now at this stage what we have is we have a desired, so we have some stable clock sources. From that we can derive arbitrary frequencies of the value that we need, and then comes the question, how do we keep the time? So that's kind of the final part, what happens out there. And this is where things get really very, very processor specific. So what I've shown out here is a particular processor. It's actually one which is used in the original embed. And I just want to show how the clocking timing system kind of looks like. So firstly, if you look at out here, it has the main oscillator to which you can attach external crystal. It has an internal RC oscillator. It's just resistor capacitor. It is very unstable, but the nice thing is it can come up extremely rapidly. It has also a provision for a real-time clock, which is separately out here. And the only thing, nice thing about it is that it is used to drive a real-time clock, and it is battery backed up. So it sits on a separate power line, and you can shut down everything else, and this thing can stay alive. And these are usually very small, low in frequency. So this is 32 kilohertz. All of this feeds into a couple of PLLs. So there is a main PLL and there is a USB PLL. USB needs its own PLL because it needs its own specific frequency of 48 megahertz. That's defined by the USB standard. The main PLL, the idea out here is that you can generate different kind of clock frequencies for it. So you can program this part and get a particular type of clock frequency that you need. And then also you notice there is something, these things also feed to this watchdog timer, which I've talked earlier in the course, that this is how if the system hangs, you can have an interrupt generated after some time. So that's the clocking part, but then within this, there are a whole bunch of, so this clock is feeding into the main processor, so that's the ARM Cortex M3. It goes into Ethernet, it goes into IOs and things like that. And then there is, as part of this somewhere out here, which I'll show, there are a whole bunch of timer registers and all where you could do things. So main characteristics of this particular processor, 3 independent oscillators. You have the main oscillator, there is an internal RC clock, and there is an RTC clock, which is on a separate power domain. Okay, so it can be kept on a coin cell battery when everything else is down. Any of these can be chosen to drive the main PLL and then eventually the CPU. So one consideration you have to take is that you can pick any one of these. Okay, and usually kind of a good one typical mode of operation is when you start up with the RC oscillator because it is very quick to up even though it's unstable. And then after some time, when your main oscillator is ready, you can switch over to that. So the idea is that you start with the IRC, internal RC oscillator, and then reset, after reset, and then switch in software to a more stable oscillator once the stable oscillator is available. RTC, this guy can wake up the processor at 1 second boundaries. So the idea is I can put the system to sleep and can set it to be woken up at a future time. It also can maintain certain amount of data and all. It's very typical. You'll find these things in PCs, and this is how kind of you can put the system to sleep and ask it to be woken up at a certain time. So right after reset, what is happening is that as soon as I power up, so you see the power line, the voltage rises. At some stage, the voltage will reach some good enough value and then become stable. If you look at the clock, the IRC clock, initially when it starts running, it's going to be very unstable. But after a short while, it will become stable, and then it has relatively, it has stable to the extent of what IRC can provide. So what is happening, so you see out here that power up and all in part take a lot of time, like in this case 60 microseconds, because we are waiting for the clocks to become stable. So one of the things which limits how rapidly you can boot up or not is often, so there are 2 things. Firstly, your voltage cannot rise up to the desired value immediately, but your clocks cannot also become stable immediately. So it always takes some time until the clock is stable, it's not getting spurious edges, things like that. So in any processor, there's always going to be this initial time when you're waiting for power and clock to stabilize before you can begin to operate. And then in this particular case, you could see that the whole boot up time of this particular thing running embed type some lightweight operating system can actually add up to kind of a good fraction of a millisecond. Okay, so by the time you're done, a lot of time is wasted. So this becomes a bottleneck, if you may, in rapidly duty cycling a processor. RTC. So in case of the real-time control, real-time clock, the main function is to maintain an absolute notion of time even when rest of the system is asleep, so that when you wake up, the system has a sense of time, how much time elapsed. And the other thing is so that you can provide functions like wake up at a particular time. Okay, so both these things are necessary. Otherwise, the system goes to sleep, wakes up, you have no knowledge of what the time is. Were you asleep for 1 day or were you asleep for 1 second? So RTC plays these kind of crucial roles. So typical RTC has some very low power oscillator, and since it needs to be low power, it's usually also low frequency as a consequence. And then it has a bunch of other things just to maintain the power supply to it, like a very low power power supply, regulator, some additional backup registers and things like that. Main thing otherwise is that it will have a 1 Hz clock, which is going to drive some registers where you maintain second, minute, hour, day, month, year, so that when the system wakes up, you actually have some knowledge of time. And then likewise, it also has some alarm registers so that you can set up an alarm so that the system is woken up or some sort of an interrupt goes out when the real-time clock meets the alarm condition. So this is how in computers and all, you can kind of set a specific wake-up time. Same thing with embedded systems. Now, the timers and all are how you begin to use these things. So almost any embedded processor which is designed properly will have a whole rich slew of So in this particular case, again for that same processor, what you see are a whole bunch of things. You'll see things like capture timers, watchdog timers, pulse width modulator, repetitive interrupt timer, and a whole bunch of things which have to do with timer counter type functionality in one way or the other. So let me kind of describe again what this particular processor has. Again, every processor is going to be unique. So this one has four 32-bit timers, external event counters. Okay, so the idea is that you have four timers available. Typically, one will be used by the operating system to provide general timing services. Others are usually available for application usage, or maybe they might be grabbed by some particular device driver or the other. They are designed to count cycles of the system-derived clock or some external clock. So you can on a per counter basis select what is the clock that they're counting. They can be programmed with a prescaler. So usually the processor clock is very rapid and it will roll over very quickly. So maybe you might want to operate on a divide by basis. So my processor may be running at 100 megahertz, but maybe for my count timer, I will like to operate at 2 megahertz. So you can specify for each one of them a particular prescaler. There are 32-bit capture channels per timer. So the idea out here is, and this is a very useful functionality, that I have some sort of external event coming. And when that event comes, I want to know precisely when it happened, because so I want to timestamp it. Now, one way of doing it would be that the event comes, it causes an interrupt, you go within the interrupt handler, you read a timer. But by that time, some time would have passed, and also if the interrupts were disabled, a lot of time would have passed. So usually they provide this capability that you can say whenever a particular watch a pin, and whenever there is an event on that pin, immediately take a snapshot of the timer. So now at most you have a 1 clock cycle error in that, right? Because an event may happen in between clock edges, so there will be a little error because of that. But other than that, there would be none. And then you can also, whenever the capture happens, then you can also cause an interrupt. So you can do very precise time stamping through this. Then there are also these notions of what are called as match registers. And kind of the idea out here is that I will let my counters, my timers count up, but when they hit a particular value, I want something to happen. So this is how I can create interrupts at arbitrary times, sleep until a particular time. So, so my counters can free run, but whenever their value matches a particular value, then an interrupt is sort of generated. And then they also bring out these things on external output, so you can easily generate periodic waveforms and things like that. You can generate waveforms that have a particular behavior. A very common interface that many devices offer is a so-called pulse width modulated interface, where the idea is, so think of like motors. So I want to control the speed of the motor. So I need to convey an analog value to it. I have to say that your speed, let's say its maximum speed is something. So I normalize it. I say that I'll call the maximum speed to be 100. And now I need to tell it what should be the desired speed. So I can say, make your speed to be 75% of the maximum. So I need to convey this analog value to it. So one way is that you can literally have a n-bit number. You output that, have a digital to analog conversion, feed it out, but then you need lots of pins for it. So what pulse width modulated waveforms do is they generate a square wave whose duty cycle is the analog value I seek to convey. So the idea would be the duty cycle is that within every period, what fraction of time the signal is high. So if the signal is always high, that means it's 100%. If the signal is always low, it's 0%. If I have a perfect square wave, which is high 50% of the time, low 50% of the time, that means 50%. So with a single pin, or whatever, one pin and the ground, I can convey an analog value. Okay, and that is called pulse width modulation. I'm changing the width of the high pulse as to correspond to the analog value I'm seeking to convey. And the way to generate these things is using counter. If you were to do it purely in a program, what you would do is you would say, set the signal to be high and wake me up in period times the analog value that I want to convey. So if I want to convey 50%, I would say wake me up after t over 2, and then bring the signal down, and then again arrange to wake up when I need to bring the signal back up. You could do it in a software intensive fashion. You'll have a lot of interrupts. You'll have a lot of interrupts happening at a very rapid rate. And this is a very commonly encountered operation. So almost every processor in the embedded world will provide you hardware support within the timers so that you can set a signal to be low or high or toggle or do nothing based upon what is happening to the whenever a counter matches a particular value. So you can generate these pulse width modulated signals very easily. They are used to control motors. They are used to control. They are actually also used the reverse direction. Many sensors send their values in a pulse width modulated waveform. So it's very common, for example, for motors to tell their position or speed using a pulse width modulated signal. So PWM signals are nice in the sense that they have digital values, 0 and 1. The value is binary, but the analog value is carried in the timing of the signal. Okay, what's the disadvantage of this approach versus carrying analog values as n bits which you convert through A to D or D to A? So I'm carrying things in a single line in the timing information. I can make the resolution. It's kind of related to that, but not quite. Well, power is certainly advantageous for PWM, right? I have a single line. Okay, it's a temporal resolution, right? I mean, in the sense that for any given frequency, let's say my processor is 100 megahertz. Okay, and let's say I want to carry. So my one cycle is well. Let me make my life simple. A processor is 1 megahertz. That means a clock cycle is 1 microsecond. Let's say I want to convey values from 1 through 100 at 1 digit resolution, right? So I want to be able to say 1, 2, 3 through 100. So that means my period of my PWM signal must be 100 microseconds, right? Because only then I can make, right? So that means I can convey a new value every 100 microsecond only, okay, every 100 clock cycles. Whereas if I was sending things as a 8-bit number, then I can keep changing it every clock cycle. So basically, if I have signals which need to change very rapidly, then I should use the bit parallel approach. But if on the other hand, I'm looking at slowly changing signals, then I can get away with a single value. And then, so literally a PWM thing is nothing but a very fancy way of a serial communication. Okay, that's what's happening. So it's temporal resolution, which is kind of the main thing. I can achieve the same bit every. And other places where you will see these things is like LED lights. Their intensity is usually pulse width modulated control. So motors, lights, these kind of usually high power sort of things which consume a lot of power. You would often see that PWM signals are used out there both to control the thing as well as for them to convey information packet. And like I said, the main thing you win is a single wire or single wire on a ground. So just a pair of wire can convey information. So accordingly, processors provide support for it. So and these kind of features help you do that. Let's see. So pulse width modulated, I mentioned. Repetitive interrupt timer. So the idea out here is that operating systems oftentimes need sort of a periodic clock tick. So most operating systems deep down have kind of like a heartbeat, and they kind of operate off that. So this repetitive timer is kind of what this processor provides specifically just for that particular purpose in a system tick. Then another one is wake up timer, and this is an interesting one. What it does is it basically allows software to make sure that main oscillator is working. So remember, at startup time, it started using the on-chip RC oscillator, which is rapid to turn on but is relatively unstable. So what this wake up timer does is it basically arranges to give, you can set it up so that an interrupt comes after a certain amount of time when clock is known to have become stable, and then you kind of transition over to that. So a bunch of special purpose registers as well. So main point behind kind of all this is that by the time you kind of see timing information in a system like this, in a typical embedded system, there's a whole bunch of things going on. So there is the resonator oscillator, whose imperfections you have to worry about. They're unstable and all. You have to set their frequency to the right thing. And then there is this interface, which this suite of timers and things like that, which the processor provides. And then finally, at the highest level would be your operating system APIs, which let you read these things. So things like sleeps, things like wake me up at a certain time, all these kind of stuff which the operating system provides to manipulate this. Processors usually have a lot more resources than the OS API is exposed to you. Usually through the OS, we only get to see kind of a simple abstraction of timing, but in embedded systems, you usually have to make use of these additional timers. So anytime you are doing any sort of a real-time system, you cannot simply rely on what the OS provides, because it is usually not sufficient. You have to directly work with these timers, counters, and deal with their interrupts and deal with the controls to kind of make effective use of them. So next part which comes up is so now I have clocks. I can read the clocks, I know the time, except that they have no bearing with time with anything else. Okay, so my system powers up, the counter will have some value, I will read them, and relative to whenever the system started running, I would have some sense of time. If I'm lucky, my clock source is very stable, good, I'll keep getting good time in the sense that I would be able to measure passage of time accurately, but I still would have no idea whether when my counter says n as the time and when another device also says n as the time, are they actually together or not? They are not synchronized. So that leads to kind of the other very important aspect of timing in systems, which is how do I relate time as seen by an independent system with time that the rest of the world or other nodes or other computers believe it to be. So you need to synchronize time. And that's what we are going to talk about down here. So, so we talked about imperfections in frequency, instability and all. But imperfection in time refers to the fact that my counter is reporting a value, which when I map to my notion of time is not corresponding to whatever my coordinate system is. I think I'm at 1 p.m. on November 20th, but maybe the actual time is 2 p.m. on November 20th. And that difference is what is called as the skew. That is the difference in time values of two clocks. And so very common case is that the second clock is the UTC. So that is the humanity agreed upon kind of notion of time. So we are really saying what is the difference between my notion of time versus kind of the agreed upon notion of time. But it doesn't have to be that way. It could simply be that I want to make sure that all nodes in a network have the same notion of time, even though that may have nothing to do with UTC. Synchronization refers to the fact that two clocks are synchronized. We say that two clocks are synchronized at a particular instant if the times that they report, that is, and by that what I mean is that after you have gone through reading the counter and mapping it to a time value, the time that I get are within some constant delta of each other. Okay, so then we will say that they're synchronized to within delta of each other. So a set of clocks will be synchronized if the worst case skew between any two clocks in them is within delta. So I can say a bunch of nodes in a network are synchronized if they all, let's say if I were to send a common signal to all of them, like some flash of light happens, they all notice it and they timestamp it, their timestamps would be within delta of each other. That's when we'll say that they're synchronized. So clock synchronization requires that each node somehow can know about what is the value at another node so that they can correct for it, right? So, and they have to be able to do it in the face of unpredictable communication delays. So that's one aspect, which is to synchronize, I need to have a sense of what other nodes think the time is so that I can correct my time. So that would be an essential part. And and like I said, I need to be able to do all of this, even though my communication with the nodes may have its own delays, may be variable and all. The other thing is, to avoid bad things from happening, any time synchronization protocol or clock synchronization protocol should never let the time run backward. it would be pretty awful if right now I check the time on my node and it said 1 p.m. and then I checked a second later, and meanwhile it checked with other nodes and decided it was running too far ahead, and it corrected it to 12:59, and now it reported 12:59 to me, and the application would think time went backward. So a good synchronization strategy should also make sure that time never goes back, because otherwise there are all sort of bad implications of that. So time synchronization is important, as you can imagine, for a variety of reasons. I mean, for example, are things happening simultaneously? What order did things happen? Did a sensor 1 reported target it observed at time t1 according to its clock? Sensor 2 reported the target at time t1 prime according to its clock. Can I be sure that they happen? What order did they happen? All those kind of questions. So ordering of events, coordinated actuation, that is, I want two nodes to do things in some particular sequence, like this node should fire first, then this node should fire, or maybe they should fire together, all those kind of questions. Logging data, what was the absolute time when something happened? Maybe I want to measure the speed and use that speed to classify the type of target it is. I want to measure performance, debugging. One very good example I was reading was that so in the stock market, so I'm sure you would have read these articles about that, how latency is a very critical thing in stock market trades. So companies try to put their computers as close to the New York Stock Exchange computers as possible, literally in the same building and all. And they have been building kind of like dedicated networks across the country just to reduce that latency and all. One of the things also is that currently the trades are logged at 1 second timestamp, but when cheating happens, the regulators are unable to construct what was the sequence so that they can detect insider trading and these kind of things, because the logs are at much coarser granularity, namely a second, whereas the algorithmic trading stuff takes place at microseconds kind of speeds now. Okay, so being able to timestamp very accurately on a nationwide or literally planet-wide basis so that you can reconstruct things that happen in a distributed system. These things are important. Another example, like a lot of signal processing and all. So for example, you often sensors detect some sort of a target. They try to identify where is the target. Well, a very common technique is that bunch of sensors are going to observe the signal, and then they are going to exchange information about when they observed it. So like for example, in this case, an animal makes a noise. That sound is heard by a bunch of acoustic sensors. They will all say that when did I hear a particular feature in the acoustic signal, and then go to match all of that, and then from that they can come up which direction the sound came from. So this is called beamforming. So beamforming, tracking, and in general a lot of other signal processing which is done. Or for example, maybe this animal was moving on a trajectory, and I want to kind of see how rapidly was it moving. So it could be like aircraft tracking, missile tracking, these kind of systems. This is an example out of Professor Kongyao's group out here, which shows that, so what they were doing were they basically had some sort of a sound generating target, and then using some other sensors, they would identify where its location is. Okay, so basically this guy emits sound, it could be a bird or something, and these guys are detecting it and using that beamforming and kind of see where in XYZ it is. And the fact that this time sync corresponds to how accurate my location is very sort of, this plot kind of attempts to show that as my time sync gets worse and worse, my error becomes worse and worse. Okay, and it's the same. The reason GPSs have atomic clock is because again we're trying to measure distance very precisely to the satellite. Even a meter error will, one of them can actually give result in an estimate of location which is tens of meters away. So time accuracy is extremely important in any sort of location task. This is an example of how these beamforming stuff works. So roughly speaking, the idea is, let's say my acoustic source was out here. So it will be sending out a waveform. That waveform will hit this sensor first, then it will hit this sensor, and then it will finally hit this sensor. And if these three were time synchronized, then they can compare their timestamps, and then they can try to figure out which direction would best explain those particular readings. If on the other hand the sensor was on this side, let's say bottom left, then the waveform will come here first, M3 will hear it first, then probably M2 and M1 will hear it at the same time. So depending upon which direction the waveform is coming, the timestamps will show that. So if I have timestamps synchronized, I can estimate the direction very well. So these kind of things all require time synchronization. This is actually another example of a system that folks in CS here had built. So what they had done was they were working with some people who was studying birds and rare animals and all. So kind of the idea was that whenever there was some particular type of sound happening, they would basically like to kind of capture that event. So in this particular case, what they had created was a system where basically there was a bunch of microphones, and they would first, so each one of their sensors, so they would go out and deploy them in a field, and for them to localize where a particular animal or a bird is, the location of these guys need to be known very precisely. And it's not an easy thing to do because GPSs themselves have 10, 20, 30 meter inaccuracy. So what these systems did was they themselves would localize each other by first emitting a sound. So one node will chirp, and then all the other nodes will hear that, and then they will exchange some radio messages, kind of, which we'll see later on, and then they will estimate distances, pairwise distances from each other, and then they will use that information to figure out where in space were they located. So by doing that mechanism, first thing is they will find their own location in a relative thing, and then once they've established their own locations using this timing information, then whenever they would hear a particular sound, they would be able to say that in their coordinate system where things are located. So this is another example. A lot of places time is used.
But even if you do this, you can only identify relative positions of each other.
Yeah. So and then what they do is that they would mark a couple of them through manual effort, basically. So you have to relate it back to the physical system. Another place time sync gets used is radios. So what this is showing is I have a sender, I have a receiver, and they need to exchange information. So what happens is, and we are looking at again kind of systems which sleep a lot to save energy. So what's happening is that at some point in time they want to rendezvous. They want to come together in time and exchange some messages. So they say, hey, let's wake up at 1 p.m. We are going to exchange messages. The problem is they know that between now and 1 p.m. Clocks would have drifted. And so the way you kind of deal with this thing is that you have to provide guard band. That is, you wake up in advance so that you are not going to miss it. So for example, if we two agree to meet at 1 p.m. but we know that our clocks may have a minute error, then to be safe, I will arrive there at 12:59 so that I don't miss the other party. That kind of concept. So guard bands are put in place because I have clock skew. And what that means is that if I can keep my clocks better synchronized, I will have better, shorter guard band. So you could imagine that kind of a trade-off emerging out here potentially, that if I spend more energy to keep clocks synchronized, either by having better clock or by talking more frequently, then I can save on the guard band, and then save the energy which goes into the guard band. So that's kind of the trade-off which ends up happening. So MAC protocols require synchrony. Duty cycling. This is kind of more broadly. So imagine a system where I have some sensor, and the sensor wakes up every so often to look out to see if there is a target there or not. So typically what would happen is every so often the sensor will wake up, collect a few samples, and based upon that sample do some signal processing, figure out, okay, is there something of interest out there? And so it sort of spends some time processing. Once in a while there will be something of interest out there, in which case it wants to send out an event. Now one way of, and then this events need to be transmitted all the way back to some receiver. And now think from a receiver's perspective. So one thing it can do is one thing the receiver can do is it can wake up it can be up all the time, and that's fine. So that whenever this rare event is sent, the receiver would be ready. The problem is that if the receiver is a base station which is plugged in, that's great, but usually it is not. Usually it is another sensor node. And one thing which comes up in short range radios is that receive also cost a lot of energy. So it's you cannot simply keep your radio up and listening, because it will be burning almost as much energy as if it was transmitting in a lot of these radios. So you want the receiver to go to sleep also. So then we are back to this situation where I have a sender which is sending a rare event. It will turn on its radio and send an event, and there is a receiver, and I cannot afford to keep the receiver up all the time. So I need to figure out a way that I am up when only at these desired period of times. So the way it is done, a very common way which is done, is the following: that we tell both the parties that we are going to communicate some every time t. Okay, so this is one of the approaches. So we duty cycle the radio. So I have node A, I have a node B, and what node A does is that it will it's periodically checking for the events from happening, and whenever it has an event to send, then it's going to send it. But the receive side is waking up periodically, and it doesn't want to miss that event. So to do this, what could be done is the following: when A has an event and it starts sending it, what it does is it starts sending the packet, and it stays online until it knows that the receive party would have woken up. Okay, so let's imagine that we both agree that we are going to duty cycle our radios at 1 minute. So every 1 minute, every node wakes up, checks for is there a message out there, and if not, quickly go back to sleep. So B is doing that, A is doing that. So this little thing is saying check the channel. Is there a message? These nodes are also engaged in sensing. So when they do have something to send, so like in this case A, what it does is when it sends the packet, it sends a long header before the packet, and this header is made as big as the gap between two polling intervals. Okay, so kind of the idea is that if this thing is long enough, then we are guaranteed that the other party would wake sometime during this period once, and then it will start listening and then receive the whole packet. So one way to, so in this particular case, I need frequency synchronization. Both parties need to have the same frequency, but I don't need time synchronization. I'm achieving time synchronization at the time I am kind of doing things. I'm coming together in time by virtue of sending this long packet out. Now, you might say, okay, so the transmission becomes very expensive, but kind of the idea is that these are rare events. So I'm better off whenever the rare event happens to send out a long packet, as opposed to keeping the receiver up for longer periods of time. So receive can be more expensive than sending, so this kind of an approach sort of wins out. So these are called polling based approaches, but kind of again basic idea is that as long as we can maintain common notion of frequencies, that is 1 minute for A and 1 minute of B are basically the same, then this strategy will work fine. An alternative strategy is instead of sending a long header, I can keep sending the same packet multiple times, and same idea that one of these packets would be heard by the receiver. But the alternative, totally different approach would be to do synchronization. So if both parties knew each other's time, not simply frequency, then they can arrange to wake up together. And then the idea is whenever this guy A has to send an event, it would wait until the next scheduled time, next time slot, and then it will send a single packet, and this guy will get the packet. Now, the pros and cons out here, as you can see, is that maintaining this time is going to cost us some message exchange, right? I cannot go to sleep for a year and wake up and maintain it. So I have to periodically communicate whether I have a message to send or not, so that I can maintain time. So a lot of protocols operate in this way, where every so often there is a heartbeat which goes out, which one node will send out, other nodes will hear, they'll all set their clocks, so that now they are moving, they have a common notion of time, so that whenever they poll at the same time, and then whenever I'm sending, I'm basically sending in that particular time slot. So I can proactively do time synchronization. I can waste some energy to maintain time, so that I don't have to spend as much energy when I'm actually communicating. Or alternatively, I can say don't maintain time, just have good frequency, but not time, and then spend more time, spend more energy in actual communication. But point behind all of this is that, as you can see, good knowledge of time and frequency has an impact upon how efficiently I can do communication, and that was kind of the main thing I wanted to get out. There's some work where people have shown that how good your clock is, that is how much the drift in it, is a major determinant on how much you can sleep in these kind of networks. That is, the better the clocks you have, the more you can sleep. But the flip side is we saw that better clocks consume more energy, and therefore I may actually end up losing, because while sleeping you still need to maintain time. And if while sleeping you need to maintain time using at a level which requires milliwatts of power, then you will end up being losing out. So you need so we are kind of in a no-win situation. You either, if you could magically have perfect time with zero energy, then literally you can sleep all the time, just wake up and start sending out the bits, and you're done. But we don't have that. We don't have perfect time. We don't have perfect frequency. So we need to spend some proactive energy doing that. And because the alternative is to have a costly clock all the time, or whatever, power-hungry clock all the time, which doesn't end up good either. So there's a trade-off which ends up happening. So to summarize, kind of, so time synchronization is useful for a variety of purposes. Question is, how do we kind of achieve that? So much like clocks themselves, ultimately, after you are done with a synchronization strategy, you still have to deal with the same kind of issues, like what is the error, what's the quality of time that I'm achieving. But here, since you're operating over network, there are other type of questions also. Over what ranges or distances do I need to maintain time synchronization? It's one thing to say every clock on Earth is synchronized to 1 nanosecond. It's another thing to say every clock in this room is synchronized to 1 nanosecond. The latter obviously is a lot easier to do than the former. So what spatial region over which synchronization is needed? Lifetime. How much, for how long do I need the synchronization for? Do I need the synchronization only for the next hour, or do I need it forever? Okay, so that time scale kind of matters. How much power am I willing to spend? How much bandwidth am I willing to spend? What are the costs? All these kind of structures end up end up being an issue. So let's look at what the state of the arts are in this thing. So GPS is kind of, although we think of it as geopositioning, but it's really geopositioning and timing systems. That's really what it is. So it gives you, all GPSs internally calculate time relative to the atomic clocks as a necessary part of localization. And in fact, many of these devices have a pin called PPS pin, 1 pulse per second pin. And essentially the idea is that the pulse on that pin is synchronized to the global time, and it's usually accurate to within a few tenths of nanoseconds. The problem is, so while ubiquitous, it is power hungry and it's outdoors only. And the other thing is, you can, if you put the GPS to sleep and then you wake it up, it takes significant amount of time before it locks into the satellites and all. So it's not something you can very quickly get a time on. You have to wait for satellites lock to happen. NTP, all our computers have it. Several milliseconds to tens of milliseconds of accuracy, but worldwide. So that's a nice thing. Okay, as long as you are hooked up to the internet and can talk to a server, time server, you are good to go. UCLA, for example, there's a machine called time.ucla.edu, which is UCLA's time server. It presumably, I believe, it has some sort of an atomic clock attached to it, or a high quality clock. And so we are literally very close to a good reference quality time. So on campus, you can achieve extremely good quality time. IEEE 1588, which is also called as Precision Timing Protocol, is basically kind of follow on to NTP in some ways, but its scope is different. It shoots for local area type time synchronization, but goes after microsecond accuracy. So you can have devices on an Ethernet or a campus LAN, for example, which are at these things. And the way it achieves it is by using special time stamping techniques, okay, which really kind of make a huge impact. And then there are a bunch of protocols in all emerged. There is one called FTSP, which are optimized for short-range wireless kind of things. So there's a whole bunch of things exist. At this stage, roughly speaking, if you're on a wired, okay, if you're willing to spend big bucks, then over a few miles distance, you can get down to picosecond type synchronization. But that is really big bucks, and the entity which is kind of pushing that quite a bit is CERN because of their atomic particle accelerator work. If you have good visibility into satellites and power is not so much of an issue, you can get nanoseconds anywhere on the planet. And you could do these things by sometimes for indoors. What people do is they put a GPS antenna outside and then run a coax cable and then kind of retransmit the signal indoors. So you could do that. NTP is tens of milliseconds, takes a long time to converge. If you start up a computer, it will not immediately give you milliseconds accuracy. It will take a few days before it hits that kind of accuracy. The reason is because they don't want hundreds of millions of computers just bombarding the internet just with the time synchronization traffic, so they pace it slowly. So it takes time for it to get that accuracy. If you are over short range radios, you can get to microsecond or even sub-microsecond now with sort of some modest effort. So let's look at some of these. Actually, given that there's only 5 minutes, okay, yeah, I'll start on it. So one very common approach to time synchronization is not to synchronize physical time, but rather to synchronize logical time. And kind of the idea is, some of my examples where I said a sensor wants to know whether it was first or the other sensor was first, I want to get the direction right and all it needs to know is whether my timestamp and the timestamp at another node, what is the logical ordering between them. I don't need to know whether the value of my timestamp minus the value of other timestamp, how many seconds it is. It's just I want to get the order right. And some of the early work really kind of focused on that. In fact, many problems in computer science really boil down to ordering, in the sense that are we synchronized, in the sense that do we have our order right or the timestamp right. So the notion out here is the following. I have a bunch of nodes and they have events happening. These red ones are events. And there are two kind of events. Some of these events are simply things like an observation they are making, a sensor event happened. So like this E21, for example, maybe this node P2 observed something from the outside. But then there are other type of events which are related to communication. So like E24 is the event where P2 is sending a message, and E12 is the event that node 1 received that message. And obviously, looking at this, one would say that one constraint has to be true is that E12 must be after E24, right? Because I cannot receive a message before sending it. So we do have a causality requirement. But so now imagine that if P1, P2, P3 had their clocks and timers internally, and they were time stamping their events according to their local clocks, then it must be the case that that whatever time value E24 was assigned to and whatever time value E12 assigned to, if I were to map them into a common time base, a system-wide clock, then E12 timestamp must be higher than E24's timestamp. And so the idea is, in a communicating system like this, each communication event gives me a constraint, and I can use that to construct ordering between these events or a partial order between these events. And that will give me a common notion of time. So looking at this, for example, if I have this one, E25, E33 out here, I do know that E25 is after E24. But looking at this, there is nothing I can say about whether E25 is before or after or at the same time as E12. And likewise, if there was an event called E32 out here, I do know E32 is before E33. But I cannot really say E32 is relationship with E12 and E25. So I cannot resolve all the ambiguities, but I can certainly resolve, establish some some partial order among these events, and that's kind of the idea. So in fact, this piece of work which I'm describing was a seminal piece of work by a guy called Leslie Lamport. Who, anyone heard of him? Why is he famous? Besides that, huh? Actually, the man behind LaTeX is not Lamport. It is Donald Knuth. It's Donald Knuth who wrote LaTeX. But anyway. Okay, fine. Okay, but okay, that okay. But what else is Lamport famous for? No one knows. How many of you are computer scientists? Some of you. What's the most famous prize in your discipline? Turing Award. Yeah, he won the Turing Award just 2 or 3 years ago, right? And he won for this work. Okay, his work on clocks. He's a distributed computing guy, but his papers on clocks are considered to be seminal. But this is logical clocks. So anyway, we'll go to pick up this thread next time I continue on this. So on Wednesday, we are going to again switch to presenting things. Again, send them my way. The remaining presentation topics, I have kind of a list sorted out, so I'm going to finalize it sometime today, maybe tomorrow,